Okay.
Okay.
Carmit, it's all yours.
Thank you. And thank you for the last-minute invitation. It's a great opportunity to speak in front of this crowd. So I'm going to present a recent work joined with Mutu and Ruhan, which is our brilliant engineer. And this work was done in the context of the DARPA SIEV project recently. And it's about Ligetron, zero knowledge on steroids. Okay, so, good. I want to start with a demo. So please use your cell phones or your computers, laptops, and go into the first, Daniel, if you can help me, I can also do it here. So, a disclaimer, I'm a theoretician. I've never done a demo as part of my talk, but you know, I'm part of a startup, so it's either, going to be a huge successful or not. But it is simple enough for you to run the demo. I promise I'm not going to steal any information from your devices.
The statement is false? Or?
Well, okay, good. No, but can they see? Were you able to copy the link? So go here. Just the first screen. This is where the prover runs, and then click download proof. So did everyone do that? Can you see the? Okay, they want to see the link. Great. It's yelkey.com/film. And it's simple enough even for theoreticians and even for wannabe cryptographers. Itai. Good. So let's hit download proof. And we have a proof. Maybe we can go back. Is it just Alt-Tab? Yeah. Cool. So, and then we have a proof.data file being stored on our device. This is the proof file. And then you can go to the second link, yelkey.com/myself.
You all got it?
For me, the input is the hash of the input string, so what is that?
I'll show you. I'll show you what's the input. I'll discuss in a second. And then, choose file. And upload the proof file. I have a great helper.
Good thing I know about zero knowledge.
Yes, that skill is really important here. Did anyone complete it? Anyone else? Just go back to the, if you need to see the link again. All right, so thank you. Thank you for helping. And yes, so what exactly did we see here? So the NP statement.
I'm a cryptographer.
Now you have a valid certificate for being a cryptographer, yes. Okay, good. So what we've seen here is a proof for an NP statement, a batched statement for 1,000 copies of an eddy distance statement. So here the witness includes two strings, and basically the validation or the statement verifies whether the eddy distance between the two strings is smaller than 5, okay? And this NP statement roughly contains 8 million gates. And the way it is done is basically through WebAssembly or VASM. As you can see, the prover You can see my mouse. The prover is receiving as an input a WASM file together with the two strings, which are the witness. And the verifier receives also a WASM file and two placeholders, okay, just to indicate the length of the strings. And you feel free to run and test it on your own strings. Just that it's not flashy enough, so just make sure that you erase the proof.data file every time so you can upload the correct one. Good. Okay. So let me discuss a little bit more about our tool chain. So we basically build an automated way, okay, to take a high-level code, right? So the coders can work with any high-level language, compile it into a WASM code, and this WASM code is being input file together with the witness to the prover, and the verifier also gets a WASM file. Okay, so it works fully automated in two ways, where in the second step, we take the WASM code and we interpret it into a set of constraints, basically what we call the extended witness. And the reason we chose, basically our great engineer Wuhan it was his idea and recommendation to work with WASM, because it has a sufficiently low-level mechanism, so it's simple enough to extract the constraints while still maintaining features of high-level languages. So here's how it looks. So basically, the coder generates, in this case, this is what we did for the demo, a C code for edit distance. Okay. The only difference from just a standard edit distance code is, where is it? Is here. We replaced if with oblivious if. Okay. Code basically needs to be oblivious. And then we used, in our case, LLVM compiler to translate the code into a WASM code. Okay, so it's like super simple for the coder or for the engineer to use high-level language, and then the system already takes care of the rest. So some key insights of why do we want to use WASM. So we take advantage of the operational semantics of WASM together with the versatility or versatile features of Ligetron to get really, really efficient, to be very, very efficient in time and space. Also, another advantage of WASM is that it has a relatively small set of instructions to compile. So it makes it much simpler to translate it into a set of constraints. There are quite plenty compilers that goes from various high-level languages into WASM, including even Solidity. And finally, WASM doesn't use system calls, okay, which makes it much easier we don't need to handle complicated code. All right, so let's talk a little bit about performance. So these are performance ran on a browser. So as you can see, the table goes from, so the left column is the length of the input, the length of the witness we have tried. So we compared 30 against 30 bit length strings, 40 and 50. We went up until 50. We haven't tried more. We plan to do that. So let's say the longest witness implies a statement or number of constraints at a size of roughly 1 billion gates. The second column is the number of constraints per instance. And then third one is the batch size. So if you want to count how many constraints we have overall, you just need to multiply the second and the third columns. And then we have the running times. And you can see that this runs really, really fast on your, let's say, local browser, on your phone. And if you want to even try to compare it to state-of-the-art implementations, this is the batch setting, but even if you look at the numbers or ballpark numbers, this could be even competitive with current state-of-the-art implementations, recent implementations like Breakdown and Orion that use much, much heavier machinery, right? For instance, here we're using, if you use your local phone, you only need to, you only have, let's say, up to 4 gigabyte RAM memory and in a single thread. And recent implementations require up to, let's say, 64 core machines and 512 gigabyte of RAM. So this is really, really both space efficient and time efficient. And it also has many features that we like from zero knowledge proof. It's non-interactive. It achieves sublinearity and plausibly post-quantum secure because it's based on the ZKProof system. Okay, so previous performance or table was when we tested that on the web browser. These are the really what we call the steroid numbers. So here we tested our implementation on heavier machine, a closer configuration to what recent implementations have been using. And you can see this is on a 32 core machines with 64 gigabyte. I just want to say that one thing I forgot to say is that our proofs achieve 128-bit security, and I guarantee you that Justin will approve our soundness analysis. So for the steroids instance, you could actually see that we get really, really amazingly fast numbers, where both the prover and the verifier run in the area of nanoseconds per gate, which is really, really fast. I mean, you can really compare the batch setting with the non-batch setting. It's not really a fair comparison, but still you can see the ballpark of the running times, and this could be even competitive against. Again, once you look, you take into account the different settings. For instance, against volley-based implementations, recent implementations, which are really, really fast. So again, all these tools are really amazing and beautiful. But this shows that you can actually get like really fast implementations, which is also space efficient. And you can also get like all the features that you would want from a zero knowledge proof, right? It is publicly verifiable, it is sublinear, it is non-interactive, and potentially also post-quantum secure. And the reason it is space efficient is because we don't really need to store the entire witness, the entire extended witness in the memory. When we build the set of constraints, we do it on the fly. We actually need to do it 3 times during our proof. And if, for instance, you would consider R1CS intermediate representation, then you wouldn't be able to store the entire extended witness in memory. For instance, if you want to run it from your cell phone. Okay, so this is really, really take advantage of the features of the way Ligetron works. Yes, I don't know if we have, we do. If you want to run, I want to show you another demo for another statement. Here we have 2 strings, okay? And what we're checking is the frequency, the number of times a substring occurs in the bigger string, okay? And here, what we're checking is whether it occurs more than twice. You can see that it occurs 3 times. So you can actually use those links if you want to run the proof. Just don't forget to erase the previous proof file from the previous iteration. Let me give you a second. You want to look at the links. Yes?
When you said sublinear on the previous slide, what
Previous slide, yes.
Yeah, what measure is sublinear referring to there? Because like the proof lengths.
Right. The number, right, the size of the overall constraints, right? The number of gates you have.
Yes, that as well. Yeah.
Yes. It's sublinear in that. Is that what you meant? Okay. All right, sorry, yes?
Isn't the rectifier constant with respect to the number of gates?
When you say constant, you mean what, constant time?
Yeah.
No, it's not. It's not constant time. In the batch setting, you can actually make the algorithm run in sublinear time because you can skip some of the checks of the actual proof system. But when you switch to the non-batch setting, you're actually slower because the way you arrange the extended witness into the blocks requires an additional check. Okay? So while we're talking about the batch setting, or maybe the non-batch setting, so I want to say that we're almost done implementing also the non-batch setting. We kind of hope to finish it before I present this, but yeah, it's not done yet. But our estimation is that it will be slower, let's say between 5 to 10x. Because there's another, as I was saying, there's another test we need to run. If you're familiar with the Ligetron internal details, this is the linear test, which you can skip in the batch setting. And we also have an optimization for what we call the quadratic test in the batch setting, which we cannot use here. So it's going to be slower. This is the estimation. Okay, so I just want to conclude. The goal is to come up, right? Our goal is not just to make, to check who's fastest, right? Or who has the best proof length. Really make zero knowledge accessible. And that also means developing tools that engineers and coders could use more easily, even if they don't have a complete and thorough background on zero knowledge. And this allows to really take your favorite algorithm, coded in high-level programming language, using some oblivious nature commands, and then just run our tools. And I just want to say that we have been working on the non-batch setting, as I was saying. Some of our next immediate goals is to actually being able to also use RAM access memory. Usually, I mean, you need to work harder if you want to use RAM access, because either you need to use oblivious RAM or other techniques that had been shown recently in the literature, because the code should be oblivious. It couldn't depend on the content of the witness or the extended witness. So this is on our to-do list. I think that was it. Yes, so that's it. And I'm here for questions. Thank you for listening. questions. I think this session is for both of us.
So the code is going to be open source, or how are you going to the code for this? Or
Yes, I think at least some of it will be open source, yes.
Is it zero knowledge?
Yes, yes, definitely.
Otherwise, 50 megabyte proof you could just send.
Yes, 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 yes. Right, so the proof length is, these are not in the area of the numbers we've seen, for instance, yesterday.
so it's zero knowledge and transparent. There is no order string, it's just the hash function.
Yes, exactly. I mean, I can explain. You hash the extended witness, the set of views. This is based on the MPC in the head technique. And then there's the challenge phase where
If you compare it to Stark, is it easy to benchmark on the same problem like to Stark?
yeah, it's a good question. The question is first of all the security level that you want to compare. But given that that you know that, I'm not sure. I mean, okay, it's not anyway apples to apples yet because this is batched. Well, they don't have batched the implementation, but also so. Maybe another thing I didn't mention is that our running times is end-to-end. It includes everything. It includes transforming the code into VASM and then into constraints and so on. And some of the other implementations, mostly also those that work based on R1CS, they don't count the generation of the extended witness and the constraints. So yes, it's hard to compare, but I don't know the answer to give you. I think.
Is there any assumptions here other than the hash function?
No. Yes. Yes.
The only thing is the hash function.
The only thing is the hash function.
You can do examples to apples. In that sense, there is no other assumptions involved.
Yes. They have a conjecture exactly. More questions? Yes.
So at least at the beginning, the prover and the verifier has to agree on the program collectively states what they want to verify.
I mean, pretty much the same what you would have if you want to agree on a circuit representation or, yes.
In that case, this is it.
Yes, exactly.
Circuit, they has to agree on the program.
Yes, yes. Okay, so thank you, and you come meet me offline.